Okay, so good afternoon, those people who've joined online. This webinar is going to cover advanced 3D printing, and this afternoon the area of advanced 3D printing we're going to talk about is metal fused filament fabrication. So I don't recognise any names who've joined the meeting, so just a quick introduction. I'm Steve Cox. I'm a 3D technologies consultant. So I'm kind of an independent advisor around 3D technologies, 3D printing, additive manufacturing, 3D design technologies. But I'm also a career education ambassador, and that's what brings me in front of you today. So it's a brief introduction about me. One of the things, first things I'd say is 3D printing with metal has probably never been easier using metal fused filament fabrication. And there's a lot of things to learn, but one of the reasons that it's easier is because it doesn't come in the way we're going to talk about now with Metal FFF, with a lot of the health and safety issues that normally surround printing with metal. So printing with metal often involves using powders or very, very high energy levels, and that comes with some inherent health and safety challenges often, which can need sizable investment to overcome. So 3D printing with Metal FFF is a really nice, easy option to take to start realizing the opportunities that are out there for 3D printing metal parts. And it can be quite low cost because often you can basically use a machine that you've already got to get involved with this, and I'll explain how as we go through the rest of the webinar. But generally speaking, you don't have to invest in very much to be able to start this journey of metal 3D printing. And if you've been printing with polymers, it's not a bad step to kind of take. So one of the things to remember is that everything that you'll be seeing on my screen as we go through this webinar was printed in my home office, which to me still seems quite amazing. You know, I get metal parts back in my hands and I think, wow, these started out life on my Ultimaker printer that's sitting right alongside me, and you know, it's printing away while I'm working on something else. So that's that kind of frames, you know, what you're going to see as we go through some of the rest of this presentation. One of the key things that's happened is there's some enablers that have come along that makes this a whole lot easier. I started using Metal FFF around 3 years ago now. It was literally just as the pandemic broke that this material first became available. But things have changed quite a lot in the interim time. It was quite a learning curve early on, and there was a lot of things to know, and there still are a lot of things to know, but a lot of things have got a lot easier. The graphic on the left is a bit of an illustration that I like to use, that 3D printing sometimes is a bit like putting a jigsaw puzzle together. The problem is sometimes is you don't know whether all the pieces are in the box to be able to complete the picture. And what's shown there is and to the right hand side as well are two what are called expansion kits, metal expansion kits, that basically allow you to build on the capabilities of a printer that you've already got. On the left hand side, an Ultimaker S5, on the right hand side a BCN 3D printer, and what's in the box is all of the pieces. So you can be certain that when you open that box, you've got every piece of that jigsaw that you need to be able to successfully start metal 3D printing. And I think that's great. And that's a really, really great improvement over these last 3 years to have this everything in a box that you can buy expansion to what you may already be doing using polymer parts. And you can actually go one step further, and Race 3D have just launched this solution, which is not just the printing side of things, but the post-processing side. So the printer's on the left. In the center, there is what's called a debinding station, and on the right is a sintering station. So if you've got the money, then you can do the entire process yourself. But what you saw on the previous slide is an expansion kit that typically costs around about £1,000 to take your existing printer to a level where you can start 3D printing these metal parts. So some very interesting enablers that have come along in recent times that really help make this a lot easier than it was. And if I just go through an example of what's in the box, this kind of shows you what's inside the Ultimaker metal expansion kit. So if I just work around from, let me just admit somebody. There we go. If I work around what's in the box from the top left-hand corner. So in the very top left-hand corner, we've got, well, let's start just below that in actual fact. So on the left-hand side in the middle, we've got the actual filament itself. So this is the metal filament that's kind of core to this entire thing, and I'll talk about the makeup of that in a minute. Just above it is what's called a support layer material, which is effectively like a ceramic material, and that has a role to play in this again that I'll explain later. At the bottom on the left-hand side, there is a soak tray in the box, which allows you to basically soak prints off the build plate when you've finished, because this is a fairly soft material and you don't want to go hacking at it like you might do with a polymer part. I'll come back to the next image in a second. If we go down the right-hand side of the image, then there are a couple of unique print cores for printing this material. There's a core that's specifically for the metal filament itself, which resists abrasion because it's a quite abrasive material. So you need a core that's going to withstand that abrasion. And then there's a dedicated core for printing the ceramic support interface material. And then down at the very bottom, you've got a very specialized version of Magic Goo bed adhesive, which is a real key to making sure that your print stays stuck to the build plate throughout the process. This is a material that does have quite a tendency to want to warp. So you do really need the right bed adhesive to make sure that it stays stuck to the build plate and you don't get any of that warping. Just in the center there to the left, where the guy is looking at the computer, this is something that kind of is in the box but isn't in the box. And what you get is an introduction booklet to metal 3D printing. And in there's an opportunity to register this metal expansion kit. And what that does is that gives you access to an online Ultimaker Academy portal, which will take you step by step through everything that you need to know to be successful with metal 3D printing. So I can really only just give you a bit of an overview in this webinar this afternoon, but if you register for the expansion kit and then you take this kind of academy learning, it's a really good way to set yourself up to be as successful as possible, as quickly as possible. So it's trying to take out the trial and error for this. It's trying to guide you into the best practices to get the absolute best out of metal FFF printing. So that's something that's kind of, like I said, it's in the box, but it's not in the box. It's a link eventually that you'll get to access online learning for this process. So these are some of the results that you can actually get. So again, you know, all of these made in my home office, which still really kind of blows my mind a little bit. So I've created very complex generative design parts and printed them using Metal FFF. On the upper right, you can see some fairly kind of standard gears, you know, engineering type of pieces, parts that again have been printed in metal. And then on the bottom right-hand side, this was a piece that I did quite a long time ago now, but it kind of illustrates the use of a metal manifold. So there's kind of 6 inlets and 1 outlet, and the the fluid is flowing through a matrix with a very high surface area, which is what you can see in the middle there. And that surface area is provided by a gyroid infill shape. So you can kind of maximize the area for heat exchange, for instance. So all of those things were Metal FFF printed in my home office, and just illustrates some of the kind of breadth of geometries that you can create using this technique. So these parts don't actually start out life like I've just shown you on that picture. They start out life being 3D printed, and they look like this. They look like a very kind of dull grey in appearance. And the filament that you're printing with is made by BASF. It's called Ultrafuse, and it's available in 2 stainless steel varieties, say 316L and a 174 pH version of stainless steel. And the makeup of that filament is around about just under 90% stainless steel powder, held together by a polymer binder. So there's a polymer, and the polymer in this case, in this material, is a material called POM, and that plastic polymer material is effectively holding the stainless steel powder in a matrix, in effect, and that's in a filament form that allows you to 3D print with it, just like you would any other filament for polymer printing. So the polymer content allows you the material to print like a polymer, even though it's got a very, very high metal content to it. So this is how they look when they come off the printer. They've got this very dull grey finish. It's not easy perhaps to see, but on a couple of models you might see a very thin layer of white visible in certain areas, and that is the ceramic support layer. And what that's doing is that's creating a barrier between the support materials for these parts and the part itself. These parts shrink when you go through the next stage, which is debind and sintering, which is effectively post-processing these 3D printed parts into the finished metal part. And as the part shrinks, you want the support material to shrink at the same rate. So the support material needs to be the same material as the model. This isn't like an option where you could use a soluble support. It needs to be the same metal that you're printing the main part with, because it needs to shrink at the same rate. But you need to ensure that those support materials don't fuse themselves to the model. And the white ceramic support material is there to create that barrier and interface that stops that fusing from taking place, and means that the support will be able to be removed from the part once it's finished. So this is how they look when they're 3D printed. The key part is, how do we then extract the polymer from these finished parts and then turn them into the final metal part? And that's a process called debind and sintering. In this case, debinding is a catalytic process. It uses a nitric acid environment to effectively extract the POM polymer. It changes the POM polymer into formaldehyde, and then that gets extracted out. So that's effectively taking the polymer content out of the parts during debinding. But this is just one particular type of debinding. There are different types of materials around, sometimes using other types of binder. So there's materials around, for instance, that you use a binder that can be dissolved using acetone. So that uses a different, it's a more chemical kind of extraction than the catalytic extraction for these materials. And there's some interesting materials around. the stainless steels are the ones that are all kind of programmed and dialed in for you to pick up and use. But if you're an education user and you want to explore some other materials, things like Inconel, tool steel, copper, talk to us at Create Education, because we've got some insights into those different materials should you want to go and experiment for yourself with something other than stainless steel. But this is where it all starts. This is the 3D printing stage of it, and this is what the parts look like when they come off the printer. So talk about the workflow involved here. The first element of the Metal FFF workflow is really assessing whether your part's suited for this particular process, because not everything is suited to Metal FFF. Size certainly matters with this process. You don't really want to be doing parts bigger than 100 millimeter by 100 millimeters by 100 millimeters. Now, that's not to say that those rules can't be broken, and I've broken them several times and not had a problem. But once you get above 100 millimeters, then shrinkage rates become a bit more unpredictable. So you might be successful, you might not be successful. Don't let that put you off. I'm always into kind of pushing the boundaries with these things. But generally speaking, the smaller the thing is, the better it will be, the more predictable it will be. And I think the best kind of way of envisaging what works best with Metal FFF is to think, would the part fit in the palm of my hand? If the part will fit in the palm of my hand, there's a pretty good chance that it will be suitable for Metal FFF in terms of size. The second consideration is whether the geometry lends itself to Metal FFF. So not all geometries might be able to be printed, and the wall thicknesses also kind of come into the equation as well. So that first stage of kind of assessment is quite critical. You need to look at it with a critical eye and say, would this suit Metal FFF? And if you're trying to do something commercially, does it make economic sense to do it this way? And there are ways of actually costing that out and then perhaps comparing it to having a part CNC machine, for instance. So once you start into this process and you've decided that the design that you've got is suitable for this method, obviously you can create the design for the part, but then something else that you can do is to do some analysis, which could be a useful thing to do with students, for instance, because this is about understanding, in the digital phase, whether this part would be successful. So on the left-hand side, there's a fluid adapter. And on the right-hand side, there's some very straightforward stress analysis that you can do, where the only load applied to this part is the force of gravity, and some very special material properties that represent the part at its absolute weakest point in the whole process. And you can understand whether the part is going to survive that particular part of the process and come out the other side successfully. So there's a really good element here of design and analysis that can be done, at the virtual stage to understand whether Metal FF is going to deliver the part that you want, and with some certainty. So that's a nice element to it, I think, especially for students. Just getting them used to looking at, as much as they can, analysis at a phase where you've not actually produced anything, and getting that level of confidence that this is going to work. So and the way this works is there are some properties published for this particular material in this particular state by BASF, and it's quite easy to set up a material properties, in this case in Fusion 360, to be able to run that analysis. It really is very straightforward. If we then move on to the slicing stage, then you've got your part design and you bring it into the slicer, and there's an awful lot of developments and improvements happened over 3 years to make this so much easier than it ever was before. And if I just stop sharing a second and switch to my Cura screen, I'm going to show you what it looks like actually in Cura itself. So when you bring the part into Cura, you go through your normal import the part, and you need to set the material for both nozzles. In this case, we've got ultrafuse 17.4 pH stainless steel in one with a CC 0.4 print core, and in the second print core we've got the support layer ceramic material with its own dedicated DD 0.4 nozzle setup. And when you slice this now, because we've got these material profiles loaded in, when I go to the preview and click on the model, what hopefully you should be able to see is you can see probably a very faint blue outline there, which represents the size of the model as it was brought into Cura. But notice the sliced part size is substantially different, and this is the scaling factor that's automatically applied to the part that accounts for the shrinkage that's going to occur when it goes through post-processing. So in this case, this material shrinks 19% in X and Y, but 25% in Z, so it's non-uniform. So you need to apply a non-uniform scaling factor to be successful with this. The reason for the difference, the reason for the non-uniformity, is that when it goes through the post-processing and the metal content starts to fuse together, gravity is having an effect on that fusing process. So it shrinks more in Z because of the effect of gravity than it does in X and Y, where it's just attraction of the metal powder that's actually causing the fusing. And this was something that you know wasn't automatic way back when I started using this. It's something you had to remember to do. It's quite easy to forget, and suddenly start printing and realize that you're printing at the size that you designed it at, and not at the size that you need it to be to account for the shrinkage rate. And now all of this is embedded into the material profile. So this scaling is automatic. It doesn't rely on you to remember anymore. All you have to do is make sure that you set the material correctly, and then when you do that, then it will apply this scaling automatically to it. It also does a lot of other things as well now that it didn't do before. So there's quite a few slicing tricks involved with this. You'll notice that this part is actually sat on a plate, and this is what's called a shrinkage plate. So if I go down to the bottom of this part, first of all, it prints about 3 millimeters thickness, not completely dense. It tries to optimize material usage by not making this a completely dense plate, but it prints a 3 mil thick plate and that's in the same metal material as the model. When it gets to that 3 millimeters height, then it lays down a single layer of the white ceramic material. And once that's laid down, then it starts to print your model. And you can also see the supports being printed here. And if I go through this model, you'll be able to see areas, if I zoom in, where it's also printing, again, this white ceramic interface material. So you can see that here. So all of that's now taken care of automatically. You don't have to set that up anymore, and that was something you had to do manually up until around about the middle of last year, when an awful lot of these improvements came in. So it's really come on leaps and bounds in terms of the slicing side of things. The scale ups there now. The material profile's got lots of slicing tweaks involved in it to make sure that that you get the optimum output, and you've got this shrinkage plate that it also prints. Now I should at this stage explain what that shrinkage plate is for. So as this part shrinks through the post-processing, it shrinks, and then you get the part dragging itself across the floor of the equipment it's being kind of processed in. So you've got a friction effect between the base of the part, which is shrinking and contracting, and the shelf that it's sat on, which is not contracting at all. and that friction, depending on the geometry, can result in some distortion of the part geometry. By printing on top of this shrinkage plate, you transfer that drag to the underside of the plate where it doesn't actually matter. So in this case, where that plate is down onto the glass build plate, that's now where all of the drag is happening. And the plate is now shrinking at the same rate in the contact areas to the part as the part itself. So because they're now shrinking together, there shouldn't be any drag and there shouldn't be any distortion of the geometry. Now, you can print some parts and get away without that shrinkage plate. It's a matter of kind of experience after a while, whether you need it or not. When you first engage with this, it's kind of a good play safe to really, you know, stick with this. And again, this plate geometry is generated all automatically. All I did with this part was effectively bring it into Cura, set the two materials I explained earlier, hit slice, and it's done all of the work for me. I've not really even had to think about it. So the slicing side of things is really easy. One of the things I get very involved is looking at the material usage. This is quite an expensive material, so you need to be looking at how much material is this going to use, and that's going to form part of your calculation as to, you know, what the cost of this part ultimately will be. So that's the slicing side of it. Like I say, substantially easier now than it was when I first started using this, and you know, I've kind of recognised how much this has developed in that intervening time. So I'm just going to go back to the presentation again, so we can carry on. So that's the slicing side of things. So you can slice the part, and then once you slice the part, you can carry on with printing it. And here's some images of parts being printed using Metal FFF. Like I said, this material prints really nicely. There's nothing difficult particularly about printing with this material, especially now the material profiles are dialed into it. And on the right hand side of this particular slide, you can see, you know, that white ceramic layer on top of the shrinkage plate for this particular part. So I've just paused this part so I could take a picture of it to show you. You've got the shrinkage plate at the bottom, you've got the white ceramic at the top, then you've got the start of the part that's being printed, and you can see the support material kind of in the center of that open C there being printed in a kind of triangular pattern. So printing is pretty straightforward, really. And on print completion, what you've got to then do is to put the glass plate, take the glass plate out of the printer and drop it in the soak tray that comes with the expansion kit in the Ultimaker kit. You just need a small amount of water in the bottom just to kind of interface with the bottom of the part, and that dissolves the adhesive, the magic adhesive that's been used to keep the part stuck down onto the plate. The reason for this, like I said earlier, is the material is a little bit soft, and it's very easy if you try to chisel the part off or take it off with a paint scraper or whatever you'd normally use to take a polymer part off the build plate. If you do that with this material, it's very easy to leave a chunk of it behind on the build plate. So, you know, patience is a virtue with this, and just take the plate off, drop it in water, and let it release itself rather than go at it. It's much better to do this stage slowly, and otherwise you could end up, you know, wasting quite a lot of material by destroying it, trying to remove it from the plate. So slow and sure wins the race with this. Just let the water do the work. So once you've created your part and you've 3D printed it, then you move on to the post-processing stage of what I've said is debind and sintering. So there's a number of terms here. What the 3D printed part is described as is a green part. So this is, as it came off the printer, it's completely untouched. It's makeup is exactly the same as the filament that it was printed in, so it's not being really changed in any way other than the geometry. So the green part is as printed. So the first stage with that green part is it goes through a debinding stage, and what debinding does is use this catalytic process, as I said earlier, to remove the polymer element of the filament. And at the end of that, you result in something called a brown part. So it's now the green part, but with all of the almost all of the polymer extracted from it, and that's what a brown part is. There is still at that stage a tiny amount of polymer present in the part. It's what's called the backbone polymer, and it's just about holding all of the metal powder together. So a brown part is almost completely powder, but with a little bit of polymer still in there holding it all together. It then goes into a sintering furnace, and the sintering furnace involves temperatures ultimately up to around 1300 to 1400 degrees centigrade to fuse the metal powder together. And there are some critical points to be aware of during this whole process. And one of those critical ones occurs in the early part of the sintering stage. And that's often called the valley of death. And at that point, all of the backbone polymer is gone. And all that effectively is left then is stainless steel powder. So the part needs to be able to hold its own weight at that stage to successfully go through the sintering process. So that's a brief overview of green part to brown part to finished part. If I just go back to the green part again, the part as printed is actually quite robust. It's not particularly fragile. They're quite easy to handle. You know, you don't have to be afraid of handling them. And that's really good because ultimately you're going to have to ship these parts, which I'll explain in a minute. But the other good thing about this robustness is it's robust, but at the same time the material's quite soft. And that means that you can do some kind of post-processing of your own before they go through this debind and sintering phase. And that could be, you could be rubbing the parts down using abrasive paper, perhaps to get rid of any layer lines. Shot blasting of parts works really well. It tends to give a part a really nice satin finish when it comes out of the final sintering process. You can do general cleanup of the parts. You can almost like carve the material, to be honest with you, because it's handleable, but it's soft. So the green part is a great time to actually try some or do some post-processing of your own and some general cleanup. When you then get to the brown part, that's in a pretty fragile state, and that simulation that I showed you earlier is about simulating the brown part strength and understanding, you know, will it withstand that final sintering process and that valley of death. So that's something to be aware of. You know, these critical points through this process you need to be aware of. The finished part that you get out of it at the end is around about 96% dense. And so it's not completely 100% dense, it's around 96% dense. There are some kind of small gaps where, you know, there might be small, very, very small gaps in between the powder particles as they fuse together. Interestingly, I've been involved with some projects with people looking to understand the vacuum capabilities of tests of the parts made this way, and they can withstand vacuums without leaking. What they can't do is withstand very, very high vacuums. So, you know, it can't cope for maybe the vacuum of space, or you know, vacuums for, say, things like compressors where the vacuum process is generating quite a high pressure that can lead to leakage. But just bear in mind that the finished part is kind of around 96, sometimes maybe up to 98% dense on completion, which is still pretty good. So the debind and sintering is something that you don't particularly have to worry about unless you particularly want to and buy the machines yourselves. But generally, we have partnered with a company in the UK called CMG Technologies, who, as it says on this slide, are an internationally renowned specialist in metal injection molding. So this same material that we're 3D printing with is used in a process called metal injection molding, which is, as it suggests, is injection molding, but using this same material. So the same material is injected into a mold in the same way a polymer is injected into a mold, and then they debind and sinter those parts and turn them into metal parts. And they're widely used in medical, aerospace, automotive, and other industrial sectors, and have been for over 20 years. So this is of this material, you know, it's quite a mature technology in a way. It's just only recently that we've had it in filament form to be able to use it in 3D printing. But generally speaking, this is quite a mature technology we're looking at here. It is, I think, about 25 years old. So CMG Technologies are based in Suffolk. They are specialists. In fact, they're probably the best people in the whole country doing this method of processing. And what you do is, once you've finished your printing, you get your parts down to them and they post-process them, and there's a cost associated with that, and that's something that I'm not going to go into here, but just to give you a brief idea of what that cost is, it gets calculated by the size of the tray that you end up using to process your parts. And a standard tray for them is 200 millimeters by 300 millimeters, so fairly similar to the size of a piece of A4 paper. And a tray is 25 millimeters deep, and whatever parts that you can get in there will get processed for around £80. So it kind of makes sense to build quite a few parts and try and fill that tray to get the best possible cost overall per part of the post-processing. If your part's above 25 millimeters, they need to take a tray out from above, and then you get charged for 2 trays. If you go above 75 millimeters, then it's 3 trays, and so on. So the post-processing cost is very much driven by volume. But that just gives you an idea for the kind of costs associated with the post-processing. And like I say, you don't have to worry about this at all, other than packing your parts up, sending them to CMG, and then waiting for them to return the parts back to you. So here's some examples again of parts that I've printed. So a bit of a collection of geometries, just to give you an idea of the kind of things that that you can produce using this method. And here's some of those same parts. You can see them released from the shrinkage plate in some cases. So you can see the shrinkage plate there, and you can see the support structures there for some of it. So you can see the parts do release cleanly away from the shrinkage plate and the support structures to leave you with the parts that you see on the screen. And this collection here just shows maybe some of the things that you can do. There's generative design parts on here. To the right hand side, there are some herringbone gears, which are really good examples of engineering where herringbone gear is very good at power transmission without creating thrust along the shaft from the gear tooth. But they're really, really difficult to make using subtractive manufacturing, and use very specialized machines to achieve it. But with 3D printing, they're really, really straightforward to manufacture. So what's on the right hand side there with those herringbone gears is a good example of using 3D printing for something that traditional manufacturing is not really good at. And on the left hand side, there's some fluid adapters, and it's probably difficult to see, but on the one that's just to the right of the one with the thread in it, there are some internal swirl vanes that have been introduced into that I designed in to create a swirl mix of what's going through that particular adapter. And the features that I've put in there are actually very difficult and would be very costly to try and machine in using CNC machining. So some geometries here that are quite complex in terms of generative design. There's some geometries that don't look that complex but are difficult from a CNC machining point of view to achieve. And that's where Metal FFF can be really beneficial. A bit of an insight into this case study of the fluid adapter, just an interesting aside. I wondered about the accuracy of a 3D printed thread using this method. Now, bear in mind, this thread is printed and it's non-uniformly scaled, so you know it doesn't look, it wouldn't work like an ordinary thread once it's printed. And I wondered whether that would be accurate once it had gone through debind and sintering. So in this case, this is a 3/8 inch, so it's an old metric, an old imperial size, 3/8 inch thread, which is about 10 millimeters in diameter. And this was printed, and I printed two versions of the adapter, one with the thread as printed and one with the allowance to basically run a die down it afterwards in a subtractive way. What I was surprised to learn when I got both of these parts back was that the die that I bought to actually do the one on the right literally flew down the one on the left. So all it did was clear out a little bit of ZC material, the sort of thing that would probably be cleared out by you screwing it into whatever this screws into anyway. Which kind of surprised me. Anybody who's ever done any polymer printing of threads knows that they tend to come out a little bit tight. But this was really accurate beyond my expectations. So this was something that kind of caught me a little bit by surprise, and I do understand the reasons why and why I shouldn't have been surprised now. And that's something I created a post around, so the reasons why. This is just another example of some case studies. This was a complete set of unique parts for a customer, a really big customer, well-known company. These were maintenance tools, specialist bespoke maintenance tools that they wanted creating. They'd had them quoted as CNC machine parts, and the cost was eye-wateringly ridiculous. I've never really got to the bottom of what the actual cost they were quoted was, but I've certainly heard, you know, kind of 4 figures and in some cases 5 figures. So involved for producing just one off of each of those things that you see on the left-hand side. And what I did was basically printed these parts, and the printed parts are on the right-hand side, and that whole set at cost price without any allowance for any margin. They printed for material and debind and sintering costs for just over £500. So that was a very, very significant saving compared to what had been quoted for CNC machining. It's not all perfect though. One of those parts had quite a significant crack in it, which is inside of that highlighted area. It's maybe not that easy to see amongst the layer lines on this picture, but there was a crack in this part. I could get a piece of paper down that crack to about a depth of 4 millimeters. Now, this is still a serviceable part because I checked the stress levels going through this, and that is a very low stressed area. So I was okay in sending that part to the customer because I think it would still do a job. So this was more of a cosmetic crack than it was a crack that was going to affect the functional performance of the part. But it's a good example of, this was a design that had been designed for CNC machining, not designed for 3D printing. No thought had been given to producing the part in this way using Metal FFF. So it was a good opportunity to kind of step back and think, well, how would I print that, and what was the reason for this crack? And some of the reason for that crack was the thickness of material in that area. There was a lot of thick material there, and that affected the debinding, and that ultimately affected the sintering, and that's when the crack opened up. So this was a good opportunity to look at this part and reimagine it for 3D printing. So this is exactly the same part now, but redesigned specifically for this process. And I've kind of smoothed out quite a lot of the material. I've taken material away where I found through the stress analysis it wasn't really doing anything. So it's a much more optimized design. And what you can see is I've kind of created an infill pattern into the kind of central part of this particular tool. Again, where I knew that the stress levels were low. So instead of printing it completely solid now, it's printed with this gyroid infill. So that's really allowed me to kind of take material out of the part. So that reduced the cost quite significantly. I think I brought the cost down by about 25%, and it's eliminated that the reason for that crack developing that I showed in the previous slide. So some opportunities with Metal FFF that you can take. We've already discussed some of them. So organic shapes is something that you can create, so generative design. Embedded cooling channels, also I mentioned earlier, you know, features internal to a part that are very difficult to machine can be really easy to introduce using this method. Functional surface textures, like I said, you can shot blast parts and get a really nice surface texture on parts. High surface areas like the gyroid infill acting as a kind of heat exchange area, again, which we've talked about. But you've also got the ability to do things like closed hollow structures. So instead of printing parts completely solid, you can print them with a kind of 15%, a 60% infill. There is a default profile in the material profile from BASF called lightweight, which allows you to effectively take a lot of material out of a part and then close it off. And that's something that you can't do with a powder machine. So trying to lightweight parts with powder means that the powder gets locked inside. If you close off, you know, all sides of it, you need to open it to allow the powder to get out. Well, with Metal FFF, you can close those hollow structures and not worry about that. So you get the benefit of the weight reduction because all you've got inside there is air inside of the infill pattern. The final opportunity is something that I've not yet tried, but keep meaning to, which is, you know, designing interlocked assemblies. So one of the advantages of 3D printing is, you know, kind of print in place assemblies of parts where you don't need to assemble them because effectively the 3D printer has assembled them for you during the process of printing. So that's an area I've not kind of fully got into yet, but that is an opportunity that exists. So the key points from the webinar really is, you know, hopefully get across a little bit that Metal FFF is now easier than ever. But you do need to take time to understand the post-processing limitations, because sometimes the 3D printing element of this is actually the easy part. And to be successful, what you need to do is really understand all the guidelines. So going through that kind of Ultimaker Academy learning is really useful and beneficial. So, you know, understand those guidelines, but they are guidelines. And I would say to people, always be prepared to test them out and test the boundaries and see where the boundaries are. So there's a good opportunity here to, you know, try through experimentation what works and what doesn't work. I think the other thing with this is design for additive manufacture, DFAM, is the key to success. So like I showed with that part earlier, you know, just replicating a part that you would normally make through CNC and then printing it this way isn't necessarily the best way of going about it. You know, with CNC machining, it generally, the more material that you take away from the billet, often means the part gets more expensive. So you tend not to remove material unnecessarily. 3D printing flips that on its head. So now you can start thinking about, where do I really need the material and where don't I need the material? Because then I can just lay down the material that I need. So replicating CNC parts isn't necessarily the best process. You need to factor into your design for additive manufacturing these debind and sintering process limitations and the things that could affect successful debind and sintering. And, I'd recommend this use of simulation to help you predict debind and sinter success. But I think all of this gives you the opportunity to take advantage of the geometric capabilities and the light weighting and the kind of things that 3D printing is really good at. And it can be an easier route to an optimized metal part than direct metal laser sintering, which is generally using powders and lasers to get to an additively manufactured or 3D printed metal part. The last thing I'd like to say is that I was involved at the back end of last year in writing a series of LinkedIn posts around some of the things that we've talked about today. I think there's around 7 or 8 posts on LinkedIn that you'll find if you search on hashtag Metal Thursdays. And on those posts, I go into some more detail on some of the things that we've talked about here. And explain some of the reasons behind some of the things, and that was kind of designed as a building series, if you like, of blog posts that help you understand the opportunities and the things involved with Metal FFF. So if you are interested, then search on LinkedIn under hashtag Metal Thursdays and take a look at what's on there. Okay, so that gets to the very end. Anybody who's online who wants to ask a question, either via chat or wants to come on and ask it directly, please do. I'm sure you've probably got some questions from what's been said or what I've said, because it's kind of impossible to get through every element of what's involved with Metal FFF in just an hour, but hopefully I've given you a bit of an overview of what's possible using this particular method.